So maximum likelihood estimation for our example, right? Using the same Kalman filter, which returns neg log likelihood. Now I'm going to call the outside function from SciPy. This is called SciPy package optimize, and I will use the function called minimize. So the code itself is very simple, right? I set my initial parameters, and then I call the minimize with my initial parameters, and I give it some boundaries. So for instance, I'm saying the variance cannot be negative, right? The lower bound is 0, upper bound is infinite, but cannot be negative, and so on. So I'll call this minimize and then get the minimum neg log likelihood, which is maximum log likelihood parameters, right? So again, as I said, I'm not minimizing my initial guesses for the state and its variance, but I'm minimizing all the other parameters, and their initial values are, for constant I'm assuming 1, and for phi I'm assuming 0.5. And then for variances of state and measurement errors, I just put 0.1. I just like made them up, just like plugged some numbers and hope that this procedure will find, the minimization routine will find optimal values. However, there are heuristics to setting these parameters. In the textbook, by the way, they're using heuristics. I'm not really using them here. I'm using one of them, I'll show. But there are heuristics. So like looking at autocorrelation function, looking at some summary statistics, you can come up with very good guesses for all these parameters. So in my case, for instance, I chose C and phi, the constant and autoregressive parameters, so that my long run mean given by C divided by 1 minus 2 is equal to 2. Why? Well, because my inflation target is 2, and I'm assuming this model will probably fit that 2%, and that's why I chose them this way. But again, you can choose phi to be not 0.5 but some other value based on, for instance, autocorrelation function analysis and so on. Now, in my Kalman filter, by the way, I did not obtain variance covariance matrix of parameter estimates. I will get optimal parameters, but not their variance covariance matrices. There is a way of doing it through something called Fisher information matrix, and Fisher information matrix can be calculated as something called Hessian of, I'm getting too mathematical here, I suppose, for a lot of you, but basically I'm saying it is possible to calculate, and it's actually not that difficult, but I didn't do it here. So if you are interested, please implement it itself. I mean, it's not super important for our purposes. We are just trying to see how Kalman filter works here. Okay, so I give you some hints on how to implement, but the idea is that when you run the minimization procedure, it will return you something called Hess-inf. So it's an inverse of Hessian matrix of the log likelihood. And that matrix can be used to estimate something called Fisher information matrix, which is one way of obtaining, or inverse of this Fisher information matrix is one way of obtaining the estimate for variance covariance matrix of the parameters. Why would we need it? We'll talk about the next, but let's optimize, right? So the code is very simple. Again, you have initial parameters, just call minimize, and then let's just print what it run, because minimize will return you res, some object which captures the results of the minimization. I'm going to just print my parameters. Right, I'm going to print my parameters, and then I'm going to chart my fit. So you see the blue is a hidden inflation, and the red dots are the observations. So the blue I received from my fitting to the data, right? So I fit to the data, and when I fit to the data, I got my result, right? So here I get my parameters, and now using these parameters I can actually let me see, once I ran my minimization, you see I'm using this X, my estimate, my filtered estimate of the inflation, and I'm printing it here, I'm charting it here. So this is a filtered estimate, and reds are observed. Now I can print my parameters and look at the long run inflation mean. Remember, it's that constant divided by 1 minus phi. And if I look at that, I find that my long run estimation is 2.5%. All right. And the last value of inflation, meaning in the Q1 2024, it's saying the hidden or whatever the inflation rate is 3%, and we know it's inflation is a bit elevated lately. Very interesting, right? So now this 252 is quite different from 2%. All right, so why is it different from 2%? Well, there could be many reasons. I'm saying, well, maybe our model is not good. Maybe our estimation is not good. Maybe I made an error in Kalman filter or in somewhere in my code so that I'm not getting optimal parameters. Or maybe feds are not doing very well. Maybe, although they say they are targeting 2% inflation, but it seems like it's about 2.5 their work, right? But also, what could be another reason is that maybe the inflation series are so noisy that like we can actually see that the estimate of the inflation rate itself is 0.65. 3% inflation and the estimate of the error is 0.6. That's quite a lot. So you see 0.6 compared to 2.252 suggests that maybe the difference between 252% and 2% is not statistically significant. So I do not know it here because why? Because I didn't estimate the variance or t-stat of this long run inflation. As a matter of fact, I didn't estimate the variances of even constant and autoregressive. Like I said, I didn't implement it in my Kalman filter, so I can't really say what is the uncertainty about this number. It says 252, but what if the error is very wide? So potentially, maybe the errors are so big that this difference is not significant, and maybe feds are doing their job right, and my model code is also correct. It could be that everything is actually wonderful, right? Now, let's look at another part of the Kalman filter approach. It's called Kalman smoother. So we saw the Kalman filter. Again, the filtering means you are predicting or you're estimating your state vector for the moment of time, using all the data up through this moment of time. Now, what Smoother does, as I said, is it uses entire data set. So you can try to estimate, have a better estimate in the middle of your data set while using entire data set. You should get a better estimate because in the filter, you're only using the left-hand side to the time period t, only the data prior to t. Now you're allowed to use the entire data set. So that's why it's called Smoother. So let us see how Smoother works. So the smoother is described in property 6.2 in the Shumway and Stauffer text, and in particular there are equations 645 through 647. You can look them up in that text. Again, I rewrote them to make them simpler, to make them fit my simple example and make my coding easier, right? So when I rewrote them, I ended up with 3 equations. So there is one equation similar to Kalman gain. So you can think of it as an inverse of Kalman gain in a way. So you're basically getting you are starting from the end, actually. So you go to the end of your data set. When you run the filter from the beginning to the end, you calculated the filtered value of the variance of your of the inflation, right? So we're at the very end of the data set. So we have this value which corresponds to the last measured value. And now using that value, we want to move backwards. So we start moving backwards from the end of the data set. And the way we do it, first we calculate this J, sort of an inverse of Kalman gain, and using that we can calculate the hidden state. So look at this hidden state. Look, we're using data n. N means superscript, means we're using entire data set. N is the last observation in our data set. So we're using all the data available to get the state for time t minus 1. Because think of this, our state at time t at the very end of my data set is using all the data set. Now we're moving one step backwards, and to do that we calculate this x and t minus 1, and it's based on our estimate of t minus 1, and you see this part where we're using the very last observation. So this x hat and t is our last observation when we're starting moving backwards, right? So, and then we will update. We get a better estimate than t minus 2, t minus 1. And the same with variance. So basically, again, we go to the very end and start moving backwards recursively. Right, so again, as I said, these are were obtained by my last Kalman filter run. So in the next cell, let's implement this code. This is going to be my smoother, and the way the code works is I just implement these three equations verbatim. It's very simple Python code, right? So I calculate my J and then my smooth X and smooth PS, and then my little chart will show you the difference, right? So here, as before, the red dots are observations. The blue line is a filtered line, and the black line is a smooth one. So, for instance, if I'm looking at this point here, I'm showing on my chart somewhere in the middle, right, of my data set, then the blue line would be using all the data on the left-hand side of this point, right, to come up with this blue line point. And the black line is a smooth version, meaning it uses entire data set to get an estimate for a state at this point. So that is the difference. Again, I repeated it 3 times. I hope you remembered it by this time. All right, that's the difference between smoothing and filtering. So these are my smoothing and filtering. Finally, let's look at the forecasting. See, we already used forecasting equations for Kalman filter. When we were running the filter, we are actually forecasting one step ahead. Every time we make one step ahead forecast, then we make an update with filtering, then we make forecast and update with filtering, right? Here. The way regression works, right? In Kalman filter. We forecast one step ahead. Here, you see, from here to one step ahead, forecast. And then we filter TT using the forecast. Sorry, here TT. So we're using the forecast to filter. Now in forecasting, we will not be filtering. We will only be using this part, forecasting. So we will use the previous forecast to advance our forecast forward. For the next T, we will use the previous forecast. So that is the difference between Kalman filter, although we already looked at the Kalman filter. That is the difference in its application to forecasting, right? So let us see. The forecasting will be, what are we doing here? Well, before getting into forecasting, I expanded my data set. So I went on, took my data set through 2024 Q1 in my case, and then I expanded it by 2 years, and then I put empty data in 2 years. After 2024 Q1, it's empty data. Well, in my case, it's not empty, it's zeros, but it's basically the same. Right, this code will put zeros in those empty data. So I did that. I got this data set, and now I'm going to forecast for these periods. So let's first look at the forecast, and then we'll look at how the code was implemented, right? So these are filtering and smoothing black line, and then the dotted line is a forecast. There's no more data in this period. I'm purely forecasting, running 2 equations of forecasting part of the Kalman filter. And you see this forecast is using a very similar basically code to Kalman filter, but it's only using first 2 equations and skip everything else. So when we do that, we get this forecast, and by looking at this forecast, we notice how dull it is, right? So we see the series themselves are very eventful, go up and down. There's like long periods during COVID going up, and then there's like some dips and so on. There's a lot going on, a lot to research. while the forecast is very, very boring convergence to some kind of a value. Well, we can guess what value it is, right? That is going to be a long run inflation target. So it seems it should remind you of some other models which we worked with if you are taking my course, and in particular ARIMA models, or rather not ARIMA but ARMA models. We know that autoregressive and moving average models produce these like boring forecasts. And this model seems to be very similar to it. Why? It's not a coincidence, I show. It's not a coincidence because the model, the simple model for inflation, which I am playing with in this video, is actually equivalent to ARMA1, autoregressive moving average 1-1 model. And we should know these models from our ARIMA lessons, right? Now, in the Shumway and Stauffer's textbook, example 6.3, called an AR1 process with observational noise, has a very similar state space model, and then they show that it corresponds to ARMA model. So there is another example 6.1.1 which goes into more detail. Basically, it shows that ARMA 1.1 and this model which I just described are equivalent to each other. There are slight differences with the model which I'm doing here versus the one in the textbook, but you can recognize it there. So basically, it's this ARIMA model is this state space model is equivalent to ARMA. Or alternatively, you could say my ARMA model can be represented, ARMA 1.1 can be represented as my state space model. Now, that is a well-known, result in state space modeling, that RMAX models, meaning autoregressive moving average model with exogenous variables, can be represented, arbitrary models can be represented as state space modeling. And we already discussed that there are reasons why to do that, like because state space modeling framework happens to be very fast, very stable, and it has some advantages, which one of them we will look later, and that is being handling missing values. Another thing I'll mention here is like when in my master's level courses in time series, when I teach ARIMA or ARMA, I do not show how to estimate ARMA models. I show how can you estimate AR model, but not the ARMA. Now actually you know how to estimate ARMA 1.1, right? Because it is the state space model and we are learning the code how to do it. So we are seeing how maximum likelihood estimation of SSM can be applied to ARMA. Now, as I said, our example is basically ARMA. So why don't we just, implement it as ARMA? So our state space example can be described as an ARMA model of the following form, right? So in example 6.1.1 in the Shumway and Stauffer text, they show that the ARMA model as this, right? So it's very simple ARMA model with just one constant. There is a constant, there's autoregressive term, and there's one moving average term. That it can be translated into this kind of state space model, and this is our state space model, right? You see we have this autoregressive component, we have a constant, and we have an error. Well, it happens so that ARMA errors, they can be combined into this error. They are independent. It basically what should I say? It shows the correspondence, basically, this equation to state space model which we were playing with so far. Okay, this is your measurement equations for YT, and this is your state equations for XT. Well, now, as I said, because this is ARMA 1.1 model, apparently, let's estimate ARMA 1.1 model with Python stats model package. Python stats model package actually has a couple of classes, and you have to be careful with it. You have to be always careful when you work with Python statistical packages. There are always some hidden traps here and there. So here there's a very subtle difference. I'll talk about it. There's a class called ARIMA, and you would imagine that class ARIMA should be the one which we want to use here, right? ARMA is basically ARIMA with integration equal to 0. But if you read the documentation of the ARIMA class, you will see that it's not going to work for us. And the reason it's not going to work for us is because in the notes they describe that if you specify your ARIMA model with class ARIMA, where you have exogenous variables, which in this case includes, well, naturally includes the constant, then it will be regression with ARIMA errors model. And that's not what we want. I actually teach it in my time series, in other time series, advanced time series course, in other parts, that regression with ARIMA errors is very different from ARIMA model. Not very different, but it is different model. It's not the same model. That's why it's not going to work for us. But if we read the documentation of another class called SARIMAX class, well, it seems like ARIMA, SARIMAX, well, SARIMAX is more complicated. Obviously, it has exogenous variables and seasonality. But guess what? ARIMA also has seasonality and exogenous variables. So it's very confusing in Python. It clearly was written by different people. But if you read the SARIMAX class documentation, then you'll see that that's going to work. Because although it is also regression with ARIMA errors for exogenous variables, in SARIMAX class, the trend or this constant is not treated as an exogenous variable. Now, you can treat this as an exogenous variable actually. When I was explaining, when I was sort of putting this into state space modeling framework, I treated it as an exogenous variable, with the exogenous variable being exactly 1, like an intercept. However, in SARIMAX class, conveniently, they treat the trend separately, this constant. And that is why this very subtle difference makes a very consequential difference for us, which is that we can use SARIMAX to estimate our model, right? So I'm going to use SARIMAX here, and you see it's just 4 lines of code. Very simple, right? So I'm going to supply my y. I'm going to supply the order of SARIMAX, which is 1, 0, 1. 0 meaning integration. We don't need integration. We need AR1 and MA1. And we want trend. If you do not specify trend C, it will not calculate the trend. So if I run this class on the same exact data set, I get these data. Look, 0.38, 0.83. So if you remember the output from Kalman filter fitting here, right? Let's look at the output. Sorry, I have to scroll a little bit, right? So MLE part, okay, where is my output? Here's my output, right? Look, 0.42, that is my constant, and 0.83 is my autoregressive part, right? So let's see. So instead of 0.42, we get 0.38, and 0.83 is 0.83. It's pretty good correspondence. And we've seen from this representation that in this ARMA, in state space model, preserves my constant and phi, doesn't do anything to them, but error part gets some modifications. But my constant and autoregressive coefficient are not changing in my state space representation. That's why I can compare directly this phi and c to ARMA estimates. They're very close. Now, I will tend to agree with this more than my own code, because my code is very simple, primitive, I should say, right? It's I wrote it in such a way that it's easy to understand for you. This is a production level code, so I'm going to venture to say that these coefficients are probably better than mine, which I received in my optimization, right? So these are probably better estimates. So if we go with these estimates, then something interesting we can do. Well, we can calculate, again, long-run inflation rate, and the long-run inflation rate happens to be 2.3 versus 2.52. So it's not much difference. It's quite close to my estimate. However, now that I'm using this framework, right, I can actually use SARIMAX results to calculate the uncertainty or the variance or standard deviation or dispersion, right? I can calculate the dispersion of my long-run inflation rate, because the SARIMAX will calculate me variance covariance matrix of all these parameters, and using these and something called delta method, I can calculate the variance of this. So the delta method is, again, is somewhat of an advanced technique in statistics. I don't teach it in my courses. I believe maybe in like advanced ones. But this method allows you to obtain the distribution or the approximate distribution of nonlinear combinations of your parameters. All right. So you can calculate using like Taylor approximation. So you can apply the delta method to obtain the variance estimate of this quantity, which is long run variance, and it's given by this long equation. Now, did I derive this myself? No. So I'm going to say the following. I got this by prompting ChatGPT. So I basically went to ChatGPT and put this prompt, and it produces this long, not long, but like a couple of pages long derivation of this formula. So that's why I do not know if this formula is correct. But when I look at it, it doesn't look wrong to me. So this formula doesn't look wrong to me. And that's why I'm just going to use it. Maybe it's incorrect. So look at this. What are these sigma square c? That is the variance of my constant parameter. And I can obtain it from ARMA. See, it's this number. It's my constant parameters variance. Now, what is this? Sigma p. That is the variance of my in this case, what I call P is my phi, is the autoregressive coefficient, right? So that is going to be this variance, 0.001, and so on. So I get the covariance of my constant and then the autoregressive coefficient. So basically I have everything, and I have my autoregressive coefficients, so I should be able to calculate this variance relatively easily, and that's what I'm doing here. I just implemented this formula. Again, I don't know, ChatGPT gave me this formula, maybe it's incorrect, but if I run that formula, I'm getting the dispersion of 0.54. So think of this, my long run mean estimate is 2.31, which is different from 2%. Fed's inflation target rate. However, look at this, the dispersion or square root of the variance is 0.54. So it's one standard deviation is 0.54. So my 2.31 is well within just one standard deviation from 2% target. So basically the difference between this long run mean 231 and the target rate of 2 is not statistically significant, is lesser than one standard deviation. And that's why basically we can say that the data which we gathered in the state space model are consistent with saying that Feds are targeting 2% inflation and that they are doing a good job. So we can rest assured that Fed is doing its at least part of its mandate, right? And that our model works. So again, I'm almost joking here. Of course, this sort of a primitive model cannot be used to make such a wide, such a deep conclusion, but it's kind of fun to play with. Okay, so it seems again our model and the data set are consistent with Fed's targeting 2% inflation. The final subject we're going to discuss in this lesson is going to be handling missing values.